Hello everyone, this is Rama. I am working as an assistant professor in ECE department at VJYEC. In the previous session, we have discussed regarding small signal analysis of a transistor amplifier. Now we are going to discuss about approximate analysis of a transistor amplifier. So, regarding the previous session, we have derived expressions for current gain, voltage gain, input impedance and output admittance. So, there we got AI, that is current gain equals to minus HF by 1 plus H naught into ZL, input impedance as HI plus HR AI into ZL, voltage gain as AI RL by ZI or else AI ZL by ZI, and Y naught output admittance as H naught minus HR HF by HI plus RS. So these are the four things what we have derived in the previous sessions, and these are the voltage gain with respect to source and current gain with respect to source. So we'll be getting the expressions like AV into ZI by ZI plus RS and AIS as AI into RS by ZI plus RS. So these could be calculated with respect to source. So whenever voltage gain is calculated, we'll be calculating with respect to impedance, that is total voltage gain into that impedance by total impedance, and here opposite resistance by total resistance. So this is all about the small signal analysis of a transistor amplifier. So now we'll be going with the approximate model. Why we are going with the approximate model means these H parameters will be changing from transistor to transistor, and hence we can make some of the approximations such that we could easily calculate, or we can go with the simplified versions of these expressions. So because of that, we can go with the approximate model. Coming with the configurations, our CE configuration is widely used because it can give high voltage gain, high current gain, moderate input impedance and moderate output admittance. So because of that, this CE configuration will be widely used. So with that CE configuration, we will be going with the approximate model. So before going to that, we'll just go with the values of this H parameter values as H11, which is input impedance, H12 reverse voltage gain, H21 which is forward current gain, and H22 output admittance. So these are the values of different configurations coming with the common emitter, common collector and common base configurations. So coming with this CE configuration, right now we will be going with the approximate hybrid model. So these values will be given by the manufacturer according to the transistor. So now we will be going with this CE amplifier approximate model. So coming with this approximate model, if we observe these two values are very small, and hence we can go with elimination of these two values, that is approximation. So now coming with the transistor model, this is exact model what we have derived in the previous session. So now in this model, we will be having all the four H parameters, that is HIE, HRE, HFE and HOE. So how can we go with this approximate model? Now we will be going with that. So coming with this, if we are going to apply KVL from here, this input voltage VB will be divided in between HIE and HRE into VC. Coming with this, HRE value is very small, that is 2.5 into 10 to the power of minus 4, and hence obviously this HIE into IB, will be dominating this HRE into VC. So obviously we could eliminate this HRE parameter. Next, coming with this, 1 by HOE is in parallel with RL. What is the value of HOE? It is 25 microamp per volt. So coming with this, 1 by HOE gives you 40 kilo ohms. This load resistance value will be in terms of like 1 kilo ohms. We already know that whenever we are going with a parallel connection, the less resistance will be the equivalent resistance. Hence, obviously we can say that we can eliminate this parameter. So by using this exact model, we will be having all the H parameters. Coming with the H approximate hybrid model, we could eliminate HRE and HOE. Hence, we have eliminated these two terms, and again we have redrawn the circuit, which is nothing but the approximate CE hybrid model. So now coming with this model, again we will be calculating all the four parameters like voltage gain, current gain, input impedance and output admittance. So Going for this, we have already calculated these 4 expressions with respect to general model, and for the CE configuration, the second suffix will be HFE. The second suffix indicates whatever the configuration we are going with. So we already know that AI equal to minus HFE by 1 plus H naught E into ZL. Now, in the approximate analysis, we have done with HOE is eliminated. That is, HOE can be equal to 0, and also HRE is also eliminated, which is approximated to a value of 0. So now we are substituting these two values. How we will be getting this? All the 4 parameters now we will be checking. So this gives you HOE equal to 0. That gives current gain AI is equals to minus HFE. Next, coming with this input impedance, we have already calculated ZI equals to HIE plus HRE into AI into ZL. Now, placing this HRE equal to 0, we will be getting ZI is equals to HIE. Next, coming with voltage gain. Coming with the voltage gain, we have derived this expression as AI ZL by ZI. You already know that AI is equals to minus HFE for approximate analysis into ZL by ZI. We got this value as HIE. Hence, the voltage gain is equals to minus HFE into ZL by HIE. Next, coming with output admittance. Coming with the output admittance, we have approximated this HOE equal to 0, and also here also we are having HRE which was approximated to 0. So 0 minus 0, it gives you output admittance as 0. Next, coming with output impedance, we already know that R0 is inversely proportional to admittance. So obviously R0 will be equals to infinity. Coming with this approximate analysis. So, till here we have calculated our output admittance as infinity. Here the output admittance will be equals to R0 dash. This R0 dash will be equals to R0 parallel RL, which is nothing but infinity parallel RL, means the output impedance will be nearly equals to RL itself. So this is all about the approximate analysis. So when can we go with the approximate analysis and when can we go with the exact analysis? So whenever the condition is HOE into RL, if this value is less than 0.1, we can go with approximate analysis. If this value is greater than 0.1 or else it is equals to 0.1, we have to go with exact analysis. So next, coming with the CE amplifier. So how this CE amplifier acts as, how this transistor in CE configuration acts as an amplifier. Right now we'll be having the transistor which is the heart of an amplifier. So it is connected in common emitter configuration. So whenever it is connected in common emitter configuration, the input is applied to the base and the output we are collecting from the collector terminal. So in order that a transistor to act as an amplifier, it must be operated in active region. So in order to operate in active region, we need a proper biasing through self-bias network, which was formed by R1, R2 and RE. So these three forms the self-bias network in order to bias the transistor in active region such that the operating point is stable and the transistor will act as an amplifier. So next, coming with RC, this is the deciding factor of the gain. If RC is increased, the gain can be increased. If the RC is reduced, the gain can be reduced because it is the pull-up resistor. Because it is the pull-up resistor. Next, this VCC, which is going to bias this base with respect to supply voltage through the resistors. Next, coming with, this is the input signal what we are going to amplify. It is applied through a source resistance and we are going with the coupling capacitors like C1 and C2. Here we are having C1 and C2 as the coupling capacitors because we are having the input signal over here and also the DC signal over here. These two signals might mixed up and we will be having an input like a mixture of AC as well as DC. The transistor will act as an amplifier and it doesn't bother whether it is an AC signal or else a DC signal. It amplifies both the signals, but we need only AC signal to be amplified, such that we will be using a coupling capacitors, because the coupling capacitor can block DC and allows only AC signals to the base. So here the AC signal is arrived and this transistor act as an amplifier and it amplifies only the AC signal. Again, at the output side, we are having this DC. And the AC signal, what it is amplified, will be mixed up over here, and you might have AC along with the DC at the output. So because of that purpose, again we are using the coupling capacitor over here, such that the DC signal will be eliminated and at the output we will be getting only AC amplified output. So this is all about the remaining part. Coming with this C3, it is known as bypass capacitor. So if you are not having this bypass capacitor, what happens? We are having the output amplified output voltage over here, which could be dropped across this RE. So now if we are not using this bypass capacitor, the voltage will be dropped across this RE and the gain will be reduced. We are using the transistor as an amplifier and the transistor acted as an amplifier. It amplified the input voltage to a maximum extent and again it is getting dropped across this RE, means there is no meaning for amplification. And again it could be connected to the base as a feedback also. So it is a problem if we are having a drop across this RE. So because of that purpose, we are using a bypass capacitor such that the signal whatever amplified over here, that will not be dropped across this RE, because it could be bypassed through this capacitor, as capacitor acts as a short circuit for AC signals. Hence we will be getting amplified output across this collector V0. So now how we are going to convert this transistor amplifier in terms of small signal equivalent model? As we are going with the AC analysis, the capacitors acts as a short circuit for AC signal. So we can short all the capacitors. Means the step 1 is to short all capacitors. Means the capacitors could be shorted like this. So whenever we are going with the short circuit of the capacitors, we need to remove RE also, because as we just discussed, whenever we are going with this short circuit of the capacitor, obviously there will be a drop across this RE. So because of that purpose, we will be eliminating this RE and connecting it to ground. Actually, in the next topic, we will be discussing if RE is present, then what happens. As of now, just we will be eliminating this RE for the purpose of exact analysis. Next, second step is, as we are going with the AC analysis, DC will be equals to 0. So here the DC is VCC and it should be connected to ground. Next, in the step 3, we will be marking base, emitter and collector, and next we will be transforming this transistor into H parameter model. Later on, we will be going with all the connections whatever we are having with respect to base, emitter and collector. So coming with the first transistor, coming with the exact analysis, we will be having HIE followed by, this is HIE, this is voltage source, that is HRE into VCE followed by, this is HFE IB, next followed by 1 by HOE. It is all about the transistor what you are having. This is base, this is collector terminal and this is emitter terminal. Now we will be going with the connections whatever we are having with respect to your circuit. So now coming with the circuit, It is the exact analysis, and so we are using all the 4 parameters. Suppose if you are going with the approximate analysis, we could eliminate this HRE into VCE and also 1 by HOE. Right now, with the emitter terminal, what are the connections we are having? Here we have connected RE to ground as well as capacitor also connected to ground. So because of that purpose, we will be connecting emitter to ground terminal. Next, coming with the base terminal, we are having 2 resistors. One resistor is connected to base and the other end of the resistor is connected to ground. Coming with this R1 resistor, it is again connected to base and other end is connected to actually VCC, but in the second step we have connected VCC to ground, and hence we can draw a single resistor and make it R1 parallel R2. Next, coming with this base, again we are having one more connection like RS. Here again we have short circuited the capacitor and we are having source resistance. This is RS, which is connected to VS. So we have now completed the connections to base. Next we will be connecting collector connections. For the collector, we are having only one connection, that is RC. The other end of the RC is connected to VCC, which was already connected to ground. So at the collector terminal, we are having RC, which is connected to other end is connected to ground. And here we will be collecting our output V0. So this is how we will be transforming a circuit into small signal equivalent model. For any of the transistor circuits, we can convert like this in terms of small signal equivalent model or else H parameter model. Next, coming with common emitter amplifier with emitter resistor. Till now we have discussed with respect to without bypass capacitor, means we have eliminated this RE for all of our analysis. But now we'll be considering this RE also and we'll be going with the analysis which is approximate analysis. So now again we'll try to convert this model in terms of approximate model initially. So first, going with the first step, here we have already eliminated the capacitors as we have short circuited. Next, coming with VCC, it should be connected to step 2, that is VCC, it should be connected to ground terminal. And in the third step, we have to mark base emitter and collector, and we need to convert this transistor in terms of H parameter equivalent model. Then we have to go with all the connections. So now initially we just draw the transistor in approximate model. Approximate model means we will be having only HIE and we will be having this is HFE IB, as we have eliminated HRE and HOE. So now mark the connections like it is base, emitter and it is collector. So as previously we have connected emitter to ground, here we have connected emitter to ground and hence we have connected directly emitter to ground terminal. So now we are having a connection over here, means emitter is connected to RE. So now we will be connecting this emitter to RE and this RE is connected to ground terminal. Next, coming with this base, we are having a connection from RS which is connected to VS and this VS is connected to ground terminal through RE. Next, coming with this collector terminal. Collector terminal is connected to load resistance. Load resistance other end is connected to VCC, which should be connected to ground terminal. So we are connecting here RL. Okay, so this is the transformation of circuit into H parameter equivalent model. So now we are converting this circuit like this, means we have just moved this emitter terminal upwards, means this is the emitter terminal and remaining all one and the same. So such that we have modified the circuit like this. Now we will be going with the analysis and we will be knowing which parameter is dependent on RE and which parameter is independent of RE. So now we already know that again we have to calculate the same parameters: current gain, input impedance, output impedance and voltage gain. So coming with the current gain, we already know that current gain is the ratio of output current to input current. So what is output current here? For common emitter configuration, the output current is IC and the input current is IB. The ratio of output current, actually it is IL. So we already know that current gain is ratio of load current to input current, that is IL by IB. So IL, IC both are equal in magnitude but opposite in direction. So you could say that IL is equals to minus IC. So because of that we have written like AI is equals to minus IC by IB. Where we are getting this IC? Through this current source, that is nothing but HFE into IB. So we have replaced this minus HFE into IB by IB again, both get cancelled and we will be left over with AI is equals to minus HFE. Means what can we infer from this? This current gain is independent of RE. Next, coming with input impedance. This input impedance is the ratio of input voltage to input current. So what is input voltage over here? This is VI. Suppose if you are going to apply this KVL over here, then we'll be getting like HIE into IB plus the current that is flowing through the emitter, we can write like IE into RE. Next, we can write this HIE into IB plus what is IE? We already know that IB plus IC into RE. That is HIE into IB plus IB into RE. Again, we already know that IC is equals to HFE into IB into RE. From all these things, we can take common as VI by IB. Means we can take common as IB and we can send it over here such that we'll be getting HIE plus 1 plus HFE into RE. So this is the input impedance of our CE amplifier with emitter resistor. Means we can say that our input impedance is dependent on RE. Next, coming with the calculation of voltage gain. Voltage gain, we have already derived an expression like AV is equals to AI into RL by ZI. So we already know that in the previous slide we have calculated this AI value as minus HFE and ZI or else RI as HIE plus 1 plus HFE into RE. Just substituting these two values over here, we will be getting the voltage gain, which is minus HFE into RL by HIE plus 1 plus HFE into RE. So we can say that again voltage gain is dependent on RE. Next, we can calculate the output admittance or output impedance. In the previous session, we have already said that whenever we are going with the output impedance or admittance, we have to make sure that source voltage must be equal to 0. So whenever we are making this source voltage equals to 0, obviously the input current IB will be equal to 0. So whenever IB is equals to 0, IC is equals to 0. Because IC is equals to HFE into IB. We already know that in order to calculate output resistance, Vs must be equal to 0. Whenever Vs equal to 0, IB will be equal to 0. Whenever IB equal to 0, output current IC will be equal to 0. So now, how we'll be calculating the output resistance? R0 will be equals to output voltage by output current. So we already know that output current is equals to 0. That implies R0 is equals to infinity. So now till here we got the output resistance as infinity. Till here it will be equals to R0 dash, which is equals to R0 parallel RL. Means infinity parallel RL. Whichever is the lowest resistance, that will be the equivalent. So obviously R0 dash will be equals to RL. So this is how we will be finding our current gain, input resistance, output resistance and voltage gain for CE with emitter resistor. Thank you.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.